What if the universe is whispering to us through signals we can barely comprehend? Imagine a cosmic conversation, not from distant stars or alien civilizations, but from objects that exist in the shadowy realm between stars and planets, brown dwarfs. These enigmatic celestial bodies, too massive to be planets yet too small to ignite as stars, have been sending out mysterious signals that defy explanation. For decades, scientists have detected strange emissions from these cosmic oddities, signals that don't fit into any known astrophysical framework. Some pulse rhythmically, others flicker unpredictably, and a few even mimic patterns that seem almost deliberate. What could these signals mean? Are they natural phenomena, or could they be something far more extraordinary? In this video, we'll dive into 25 of the most baffling signals ever detected from brown dwarfs, each one a puzzle waiting to be solved. From the faint whispers of distant giants to the eerie echoes that seem to repeat like a cosmic melody, these signals challenge everything we think we know about the universe. So, are you ready to explore the mysteries of the cosmos? Stay with us, because by the end of this journey, you might just find yourself questioning what's really out there. Now, let's turn our attention to the first of these mysterious signals, a discovery that has left scientists both intrigued and puzzled. Known as the Whispering Giant, this faint yet persistent radio emission was detected from a brown dwarf located in the Orion constellation. Unlike the chaotic bursts or erratic pulses we might expect from such objects, this signal stands out for its unusual frequency patterns. It doesn't match any known natural emissions from brown dwarfs, which typically produce radio waves through processes like magnetic field interactions or atmospheric turbulence. Instead, the Whispering Giant's signal is steady, almost rhythmic, as if it's following a pattern that defies our current understanding of these celestial bodies. What makes this signal even more baffling is its persistence. While most emissions from brown dwarfs are sporadic or short-lived, this one has been detected repeatedly over time, suggesting a source that remains active and consistent. Scientists have proposed various explanations, from unknown atmospheric phenomena to interactions with nearby objects, but none fully account for the signal's unique characteristics. Could it be the result of a natural process we've yet to discover, or is there something more extraordinary at play? The Whispering Giant continues to challenge our understanding of brown dwarfs, reminding us just how much we still have to learn about the cosmos. As we move forward, this signal sets the stage for the even more perplexing mysteries we're about to explore. Each one, like the Whispering Giant, invites us to question what we know and imagine what might be possible in the vast, uncharted reaches of space. Now, let's dive deeper into the theories surrounding the Whispering Giant, the mysterious signal that continues to defy explanation. Scientists have proposed several possibilities to account for its unusual behavior, each offering a unique perspective on what might be happening within or around this brown dwarf. One leading theory suggests that the signal could be the result of plasma interactions within the brown dwarf's atmosphere. Plasma, a highly charged state of matter, is known to produce radio emissions under certain conditions. If the plasma in the brown dwarf's atmosphere is behaving in an unexpected way, it might generate the steady, rhythmic pattern we've observed. However, this explanation doesn't fully account for the signal's persistence and consistency, leaving room for further investigation. Another intriguing possibility involves interactions with nearby objects. Brown dwarfs often exist in systems with other celestial bodies, such as planets or companion stars. If the Whispering Giant is interacting with a nearby object, perhaps through gravitational forces or magnetic fields, it could produce the unusual signal we've detected. This theory is supported by the fact that some brown dwarfs are known to have strong magnetic fields, which can influence their surroundings in complex ways. Yet, even this idea falls short of explaining why the signal remains so steady over time. Unlike the more erratic emissions typically associated with such interactions, Then there's the more controversial theory, the idea that the signal could have an artificial origin. While this suggestion often sparks debate, it's worth considering given the signal's unique characteristics. Could the whispering giant be a deliberate transmission, perhaps from an advanced civilization attempting to communicate across the cosmos? This idea, while speculative, isn't entirely dismissed by the scientific community. After all, the search for extraterrestrial intelligence has long focused on identifying signals that stand out from natural phenomena. The whispering giant, with its steady and patterned emission, certainly fits that description. However, without more evidence, this theory remains in the realm of speculation. As we explore these theories, it's clear that the whispering giant challenges our understanding of brown dwarfs and the processes that govern them. Whether the signal is the result of natural phenomena we've yet to fully understand or something more extraordinary, it serves as a reminder of how much we still have to learn about the universe. With each new discovery, we're prompted to rethink our assumptions and expand our knowledge, making the study of these mysterious signals all the more fascinating. Next, we'll turn our attention to another enigmatic signal, one that pulses at irregular intervals, adding yet another layer of mystery to the story of brown dwarfs. Now, let's shift our focus to another fascinating signal that has left scientists scratching their heads, the pulsating enigma. This rhythmic signal, detected from a brown dwarf in the Cygnus region, pulses at irregular intervals, creating a pattern that defies our current understanding of these celestial objects. Unlike the steady, consistent emissions we've come to expect from brown dwarfs, the pulsating enigma behaves unpredictably, flickering on and off in a way that seems almost deliberate. This irregularity has sparked intense curiosity, as it challenges what we know about the behavior of brown dwarfs and the role of their magnetic fields. At the heart of this mystery is the question of what could cause such a signal. Brown dwarfs are known for their strong magnetic fields, which often produce radio emissions. However, these emissions typically follow a more predictable pattern, influenced by the dwarf's rotation and internal processes. The pulsating enigma, on the other hand, doesn't align with these expectations. Its irregular pulses suggest that something unusual is happening, either within the brown dwarf itself or in its immediate environment. One possibility is that the magnetic field of this particular brown dwarf is interacting with another object, such as a nearby planet or companion star, creating disruptions that result in the erratic signal. Alternatively, the pulses could be caused by internal processes we've yet to fully understand, such as fluctuations in the dwarf's atmosphere or magnetic activity. What makes the pulsating enigma even more intriguing is how it contrasts with other signals we've observed. While some brown dwarfs emit steady radio waves or occasional bursts, this signal stands out for its rhythmic yet irregular nature. It's as if the brown dwarf is sending out a coded message, one that we're still struggling to decipher. This has led some researchers to speculate about the possibility of more complex magnetic interactions or even the presence of unknown phenomena within the brown dwarf's atmosphere. Could there be processes at work that we've never encountered before? The answer remains elusive, but the pulsating enigma serves as a powerful reminder of how much we still have to learn about these enigmatic objects. As we continue to study this signal, one thing is clear: the pulsating enigma is pushing the boundaries of our knowledge. It challenges us to rethink our assumptions about brown dwarfs and the forces that shape their behavior. Whether the signal is the result of natural processes or something more extraordinary, it underscores the complexity of the universe and the endless possibilities for discovery. Next, we'll explore how magnetic fields play a crucial role in shaping the signals we observe from brown dwarfs, shedding light on the mechanisms behind these mysterious emissions. Now, let's take a closer look at the role magnetic fields play in shaping the signals we observe from brown dwarfs. These celestial objects, often referred to as failed stars, are known for their powerful magnetic fields, which can be thousands of times stronger than those of planets like Earth. These fields are generated by the movement of charged particles within the brown dwarf's interior, creating a dynamic environment that can produce a variety of emissions, including the pulsating signals we've been discussing. Magnetic fields in brown dwarfs are thought to be responsible for many of the radio emissions we detect. As the dwarf rotates, its magnetic field interacts with its atmosphere, generating bursts of energy that can be picked up by telescopes here on Earth. However, the Pulsating Enigma's irregular pattern suggests that there's more to the story. Unlike the steady, predictable emissions we typically associate with magnetic activity, this signal's rhythmic yet erratic behavior points to a more complex interplay of forces. One possibility is that the magnetic field of this particular brown dwarf is interacting with another object in its vicinity, such as a planet or a companion star. These interactions could create disruptions in the magnetic field, leading to the irregular pulses we observe. For example, if a planet orbits close to the brown dwarf, its gravitational pull might distort the dwarf's magnetic field, causing it to flicker in unexpected ways. Alternatively, the pulses could be the result of internal processes, such as fluctuations in the dwarf's atmosphere or changes in its magnetic activity over time. Another intriguing aspect of magnetic fields in brown dwarfs is their potential to produce auroras, similar to the northern and southern lights on Earth. These auroras occur when charged particles from the dwarf's atmosphere collide with its magnetic field, creating bursts of light and radio waves. While this phenomenon could explain some of the emissions we detect, it doesn't fully account for the Pulsating Enigma's unique pattern. This leaves scientists wondering whether there are other, as yet undiscovered mechanisms at play. Despite decades of research, there are still significant gaps in our understanding of how magnetic fields operate in brown dwarfs. For instance, we don't fully know how these fields are generated or how they evolve over time. Additionally, the relationship between a brown dwarf's magnetic field and its atmosphere remains poorly understood. These uncertainties make it challenging to explain signals like the Pulsating Enigma, which defy our current models and expectations. As we continue to study these mysterious objects, one thing is certain: magnetic fields are key to unlocking the secrets of brown dwarfs. They not only shape the emissions we observe, but also provide clues about the internal processes and external interactions that define these enigmatic objects. By exploring the role of magnetic fields, we're not just solving the mystery of the Pulsating Enigma, we're also gaining a deeper understanding of the universe itself. Next, we'll turn our attention to another puzzling signal, the silent scream, a sudden burst of energy that has left scientists searching for answers. Now, let's shift our focus to a signal that has left scientists both fascinated and baffled: the silent scream. Detected by the Arecibo Observatory, this signal stands out for its dramatic nature, a sudden, intense burst of energy that vanishes into complete silence, leaving no trace behind. Unlike the rhythmic pulses or harmonic patterns we've explored so far, the silent scream is a one-time event, making it even more mysterious and difficult to study. The Arecibo Observatory, known for its groundbreaking contributions to radio astronomy, first picked up this signal in the late 1990s. At the time, researchers were scanning the skies for unusual emissions from brown dwarfs when they detected an incredibly powerful burst of radio waves. The energy spike was so intense that it briefly overwhelmed the observatory's instruments, but just as quickly as it appeared, the signal disappeared, never to be detected again. This fleeting nature has made it nearly impossible to gather additional data, leaving scientists with more questions than answers. What makes the silent scream particularly intriguing is its abruptness. Most signals from brown dwarfs, whether pulsating or flickering, tend to follow some kind of pattern or repeat over time. But this burst was entirely unique, a single, explosive event followed by absolute silence. Some researchers have speculated that it could be the result of a catastrophic event, such as a massive flare or a collision with another object. Others suggest it might be linked to a sudden release of magnetic energy, similar to a solar flare but on a much larger scale. However, without further observations, these theories remain speculative. Another challenge in understanding the silent scream lies in its rarity. One-time signals like this are incredibly difficult to study because they offer no opportunity for follow-up observations. Unlike recurring signals, which can be monitored and analyzed over time, the silent scream is a fleeting glimpse into a phenomenon we may never fully understand. This has led some scientists to wonder whether similar events have occurred elsewhere in the universe but went unnoticed due to the limitations of our technology. The Arecibo Observatory's detection of the silent scream also highlights the importance of continuous monitoring in astronomy. Had the observatory not been actively scanning the skies at that precise moment, this extraordinary event might have gone undetected entirely. It serves as a reminder of how much we still have to learn about the universe and the unexpected phenomena that await discovery. As we ponder the mysteries of the silent scream, it's clear that this signal represents more than just a scientific puzzle. It's a testament to the unpredictable nature of the cosmos and the limits of our current understanding. What caused this sudden burst of energy? Why did it vanish without a trace? And could similar events be happening elsewhere, hidden in the vast expanse of space? These are the questions that drive astronomers to keep searching, pushing the boundaries of what we know. Next, we'll explore another enigmatic signal, the harmonic echo, a pattern so precise it resembles a cosmic melody. Now, let's take a closer look at burst signals in astrophysics and how the silent scream fits into this broader category. Burst signals are some of the most intriguing and mysterious phenomena in the universe. They are characterized by sudden, intense releases of energy that last for mere milliseconds to a few seconds before fading away. These bursts can come from a variety of sources, and each type offers a unique glimpse into the extreme conditions of the cosmos. One of the most well-known types of burst signals is the fast radio burst, or FRB. These are incredibly powerful radio wave emissions that originate from distant galaxies. Like the silent scream, FRBs are fleeting and unpredictable, often appearing just once and vanishing without a trace. However, some FRBs have been observed to repeat, giving scientists a rare opportunity to study them in greater detail. The origins of FRBs are still debated, with theories ranging from highly magnetized neutron stars to collisions between dense objects like black holes or neutron stars. Another type of burst signal is the gamma-ray burst, or GRB. These are the most energetic explosions in the universe, releasing more energy in a few seconds than our Sun will emit in its entire lifetime. GRBs are typically associated with the collapse of massive stars or the merging of neutron stars. While they are much more energetic than the silent scream, they share a similar characteristic, their sudden and explosive nature. Both phenomena challenge our understanding of how energy is released in the universe and what processes can produce such extreme events. What sets the silent scream apart from these other burst signals is its source, a brown dwarf. Unlike FRBs and GRBs, which are often linked to highly energetic objects like neutron stars or black holes, brown dwarfs are relatively quiet and low energy compared to their stellar counterparts. This makes the silent scream even more puzzling. How could an object often described as a failed star produce such a powerful burst of energy? This question has led scientists to reconsider what we know about brown dwarfs and their potential for extreme activity. The study of burst signals like the silent scream, FRB, and GRBs also highlights the challenges of observing transient events in space. These phenomena are often unpredictable, lasting only a fraction of a second, which makes them incredibly difficult to detect and study. Advances in technology, such as more sensitive telescopes and faster data processing, are helping astronomers catch these fleeting events more frequently. Yet, even with these tools, many burst signals remain shrouded in mystery. As we compare the silent scream to other burst signals, it's clear that this phenomenon is part of a larger puzzle in astrophysics. Each burst, whether from a brown dwarf, a distant galaxy, or a collapsing star, offers a piece of the cosmic puzzle. By studying these events, scientists hope to uncover the underlying mechanisms that drive such explosive releases of energy and, in turn, deepen our understanding of the universe's most extreme environments. With this context in mind, let's turn our attention to the next signal on our list, the harmonic echo. This signal, with its precise and repeating pattern, stands in stark contrast to the chaotic nature of burst signals, offering a completely different kind of mystery to unravel. Now, shifting our focus to a signal that feels almost like a cosmic melody, we encounter the harmonic echo. Unlike the chaotic and explosive nature of burst signals, this emission stands out for its precise, repeating pattern that resembles a musical scale. Discovered by astronomers using the Green Bank telescope, the harmonic echo was first detected emanating from a brown dwarf in the constellation Lyra. What makes this signal so fascinating is its rhythmic consistency, as if the universe itself were playing a tune. The harmonic echo is characterized by a series of evenly spaced pulses, each separated by a fixed interval. This regularity is highly unusual for brown dwarfs, which typically emit irregular and sporadic signals. The pattern is so distinct that it has been compared to the notes of a musical scale, with each pulse representing a different note in the sequence. This has led some researchers to describe it as a kind of cosmic symphony, though its origins remain a mystery. One of the most intriguing aspects of the harmonic echo is its contrast to other brown dwarf emissions. While most signals from these objects are chaotic and unpredictable, the harmonic echo's orderly pattern suggests a different underlying mechanism. Some scientists speculate that it could be caused by interactions between the brown dwarf's magnetic field and its atmosphere, creating a kind of natural oscillator. Others have proposed that it might be the result of a resonant cavity within the brown dwarf structure, amplifying certain frequencies in a way that produces this harmonic effect. The discovery of the harmonic echo has sparked a wave of excitement in the astronomical community. Its unique characteristics challenge our understanding of brown dwarfs and their potential for producing complex emissions. It also raises questions about whether similar signals could exist elsewhere in the universe, waiting to be detected. Could this be a rare phenomenon, or is it a glimpse into a broader class of harmonic signals that we've yet to uncover? As we delve deeper into the harmonic echo, it's worth considering how this signal compares to others we've explored. While burst signals like the silent scream are fleeting and explosive, the harmonic echo is steady and rhythmic, offering a completely different kind of mystery. This contrast highlights the incredible diversity of signals that brown dwarfs can produce, each revealing a new facet of these enigmatic objects. With the harmonic echo still echoing in our minds, let's turn our attention to the next signal on our list, the ghostly flicker. This signal, with its unpredictable on and off behavior, presents yet another layer of intrigue in the ongoing quest to understand the mysteries of brown dwarfs. Now, as we explore the intriguing possibilities behind the harmonic echo, one question stands out. Could this rhythmic pattern be a natural phenomenon, or does it suggest something more intentional? This debate has sparked intense discussions among scientists, with theories ranging from the purely natural to the tantalizingly speculative. On one hand, natural explanations for the harmonic echo focus on the complex interactions within brown dwarfs themselves. Some researchers propose that the signal could be the result of magnetic field oscillations, where the brown dwarf's magnetic field interacts with its atmosphere in a way that creates a stable, repeating pattern. This process, known as magnetohydrodynamic oscillation, could act like a cosmic tuning fork, producing the harmonic frequencies we observe. Another natural theory suggests that the brown dwarf's internal structure might contain resonant cavities, amplifying specific frequencies and creating the musical-like pattern. These ideas align with what we know about brown dwarfs, but they also highlight how much we still have to learn about these objects. On the other hand, the possibility of an artificial origin has captured the imagination of both scientists and the public. Could the harmonic echo be a deliberate signal, perhaps a form of communication from an advanced civilization? While this idea is far more speculative, it's not entirely dismissed. The signal's precise, repeating pattern is unlike anything we've seen in nature, leading some to wonder if it could be a kind of cosmic beacon. If true, this would be one of the most profound discoveries in human history. However, the scientific community remains cautious, emphasizing the need for more evidence before jumping to such extraordinary conclusions. The debate between natural and artificial origins isn't just about the harmonic echo, it's about how we interpret the universe itself. If such signals are natural, they reveal new and unexpected behaviors of brown dwarfs, expanding our understanding of these mysterious objects. If they're artificial, they could fundamentally change our place in the cosmos, suggesting that we're not alone. This tension between the known and the unknown is what makes the harmonic echo so captivating. As we consider these possibilities, it's worth noting that the search for harmonic signals isn't limited to brown dwarfs. Similar patterns have been detected in other parts of the universe, though none as distinct as the harmonic echo. This raises the question, are we looking at a rare anomaly, or is this a glimpse of a broader phenomenon that we're only beginning to understand? The answer could reshape our understanding of both brown dwarfs and the universe at large. With the harmonic echo continuing to echo through the scientific community, our journey through these unexplained signals takes us to the next mystery, the ghostly flicker. This signal, with its erratic on and off behavior, adds yet another layer of intrigue to the enigmatic world of brown dwarfs. Now, shifting our focus to another baffling signal, we encounter the ghostly flicker, a phenomenon that has left scientists scratching their heads. Detected by the Very Large Array, this signal behaves unlike anything we've seen before. It flickers on and off in an erratic, unpredictable manner, defying the typical activity cycles associated with brown dwarfs. Brown dwarfs, often referred to as failed stars, are known for their relatively stable emissions with occasional flares or bursts of energy. However, the ghostly flicker doesn't fit this pattern. Instead of following a predictable rhythm, it appears and disappears at random intervals, sometimes vanishing for long periods before reappearing without warning. This irregularity challenges our understanding of how these celestial objects behave. One possible explanation for the ghostly flicker lies in the complex interplay between a brown dwarf's magnetic fields and its atmosphere. Magnetic fields can sometimes trap charged particles, creating pockets of energy that release sporadically. This could explain the flickering behavior, as these energy pockets might discharge unpredictably, causing the signal to appear and vanish. However, this theory doesn't fully account for the extreme irregularity of the ghostly flicker, leaving room for other possibilities. Another intriguing idea involves interactions with nearby objects, such as planets or debris orbiting the brown dwarf. If a planet or a cloud of material passes between the brown dwarf and our telescopes, it could temporarily block or distort the signal, creating the flickering effect. Yet, this explanation also falls short, as the timing and intensity of the flickers don't align with known orbital patterns. The ghostly flicker's unpredictability raises even more questions about the nature of brown dwarfs. Could this signal be a sign of an entirely new type of activity, one that we haven't yet observed or understood? Or is it a rare anomaly, a fleeting glimpse into a process that occurs only under specific, unknown conditions? Whatever the case, the ghostly flicker reminds us that brown dwarfs are far more complex and mysterious than we once thought. As we continue to unravel the secrets of these enigmatic objects, the ghostly flicker stands as a testament to the surprises the universe still holds. And with this mystery still flickering in the background, our exploration leads us to the next signal, the cosmic Morse code, a pattern that has sparked both curiosity and debate among researchers. Now, let's take a closer look at the mechanisms that might be behind these flickering signals. One of the leading theories involves atmospheric disturbances on the brown dwarf itself. Just like Earth's atmosphere can create weather patterns that affect radio signals, brown dwarfs have turbulent atmospheres filled with swirling gases and magnetic activity. These atmospheric storms could generate bursts of energy that flicker in and out, creating the erratic patterns we observe. However, the sheer unpredictability of the ghostly flicker suggests that these disturbances might be far more chaotic than anything we've seen on Earth or even on other stars. Another possibility is the interaction between the brown dwarf and nearby objects, such as planets, asteroids, or even clouds of cosmic dust. If a planet or debris field orbits the brown dwarf, its gravitational pull or physical presence could disrupt the dwarf's magnetic fields or block its emissions temporarily. This could explain why the signal flickers. When the object moves out of the way, the signal reappears. Yet, as we've seen, the timing of these flickers doesn't match known orbital patterns, leaving scientists to wonder if there's something else at play. A more exotic idea involves the brown dwarf's magnetic fields interacting with its own atmosphere in unexpected ways. Magnetic fields can trap charged particles, creating pockets of energy that build up and release sporadically. These releases could produce the flickering effect, but the irregularity of the ghostly flicker suggests that this process might be far more complex than we currently understand. It's also possible that the brown dwarf is undergoing a rare or previously unseen type of activity, one that defies our current models of stellar behavior. Finally, some researchers have speculated that the flickering could be caused by external factors, such as interference from other cosmic phenomena. For example, a passing star or a distant black hole could distort the signal as it travels through space, creating the illusion of flickering. While this idea is intriguing, it's difficult to prove without more data, leaving it as one of many possibilities in the ongoing investigation. The ghostly flicker serves as a reminder that even the most studied objects in the universe can still surprise us. As we continue to explore these flickering signals, we're not just learning about brown dwarfs, we're uncovering new layers of complexity in the cosmos itself. And with that, we turn our attention to the next mystery, the cosmic Morse code, a signal that has sparked both fascination and debate among astronomers. Now, shifting our focus to another intriguing mystery, we come to signal 6, known as the cosmic Morse code. This signal, detected from a brown dwarf in the Lyra constellation, has captured the attention of astronomers worldwide due to its uncanny resemblance to Morse code patterns. Unlike the erratic flickers of the ghostly flicker, this signal appears to follow a structured rhythm with bursts of energy that seem to form distinct sequences. The discovery was made by a team using the Green Bank telescope, who initially thought they might have stumbled upon a technical glitch. However, further analysis confirmed that the pattern was indeed coming from the brown dwarf itself. What makes the cosmic Morse code so fascinating is its precision. The signal alternates between short and long pulses, much like the dots and dashes used in Morse code. This has led to a flurry of excitement among researchers as it raises the tantalizing question, could this be a deliberate attempt at communication? While the idea of extraterrestrial intelligence is often met with skepticism, the structured nature of this signal has sparked serious debate. Some scientists argue that it could be a natural phenomenon, perhaps a result of the brown dwarf's magnetic fields interacting with its atmosphere in a way that creates rhythmic pulses. Others, however, are more open to the possibility that we might be witnessing something far more extraordinary. The discovery of the cosmic Morse code has also reignited interest in the search for extraterrestrial intelligence, or SETI. Researchers are now analyzing the signal in greater detail, looking for any hidden patterns or repetitions that might hint at a message. While no definitive conclusions have been reached, the signal has already become a cornerstone in the ongoing discussion about the potential for life beyond Earth. It serves as a reminder that the universe is full of surprises, and sometimes those surprises come in the form of a cosmic tap code that challenges our understanding of the cosmos. As we continue to unravel the mysteries of the cosmic Morse code, one thing is clear: this signal has opened up new avenues of exploration and debate. Whether it's a natural phenomenon or something more, it's a testament to the endless wonders waiting to be discovered in the vast expanse of space. And with that, we move forward to our next enigma, the phantom pulse, a signal that appeared only once and vanished without a trace, leaving scientists with more questions than answers. Now, as we delve deeper into the cosmic Morse code, the question on everyone's mind is, could this signal actually carry a message? The idea of decoding a potential communication from a brown dwarf is both thrilling and daunting. The structured nature of the signal, with its short and long pulses, has led some to wonder if it's more than just a cosmic coincidence. Could this be an attempt by an intelligent civilization to reach out across the vastness of space? Or is it simply a quirk of nature, a fascinating but unintentional pattern? One of the biggest challenges in interpreting this signal lies in its ambiguity. While the Morse-like rhythm is striking, it doesn't immediately translate into a clear message. Morse code, as we know it, is a human invention designed to encode letters and numbers into sound or light pulses. Applying this framework to a signal from a brown dwarf assumes that any potential sender would use a similar system, a big assumption, given the vast differences in technology and communication methods that might exist beyond Earth. This raises the question, even if the signal is intentional, how do we begin to decode something that might operate on principles entirely foreign to us? Another hurdle is the sheer complexity of the signal. While it appears structured, the patterns are not perfectly consistent. Some pulses are slightly longer or shorter than expected, and there are occasional gaps that don't fit neatly into the Morse code framework. This variability could be due to natural processes, such as turbulence in the brown dwarf's atmosphere or interference from surrounding space debris. Alternatively, it might be a deliberate feature designed to test our ability to recognize and interpret complex patterns. Without more data, it's impossible to say for sure. Scientists are also grappling with the possibility that the signal might not be a message at all, but rather a byproduct of some unknown astrophysical phenomenon. Brown dwarfs are known for their intense magnetic fields and turbulent atmospheres, which can produce a wide range of emissions. It's possible that the cosmic Morse code is simply a new type of natural signal, one that we haven't encountered before. If that's the case, decoding it would require a deeper understanding of the physical processes at play, rather than searching for hidden meanings. Despite these challenges, the search for meaning continues. Researchers are using advanced algorithms to analyze the signal, looking for repeating sequences or mathematical patterns that might hint at intentional design. They're also comparing it to other known signals from space, both natural and artificial, to see if there are any similarities. While progress is slow, the effort itself is a testament to humanity's curiosity and determination to uncover the secrets of the universe. As we ponder the possibilities, one thing is certain: the cosmic Morse code has sparked a new wave of exploration and imagination. Whether it's a message from an alien civilization or a natural phenomenon waiting to be understood, it reminds us that the universe is full of mysteries that challenge our assumptions and push the boundaries of what we know. And with that, we turn our attention to the next enigma, the phantom pulse, a signal that appeared only once and left scientists with more questions than answers. Now, shifting our focus to another intriguing mystery, we encounter the phantom pulse, a signal that appeared just once, vanishing as quickly as it arrived. This fleeting burst of energy has left scientists scratching their heads, as its brief existence defies everything we know about the behavior of brown dwarfs. Unlike the rhythmic patterns of the cosmic Morse code, the phantom pulse was a solitary event detected by a radio telescope during a routine scan of the sky. It lasted mere milliseconds, but its intensity was enough to capture the attention of researchers worldwide. What could have caused such a sudden and isolated emission? And why has it never been observed again? One of the most puzzling aspects of the phantom pulse is its unpredictability. Most signals from brown dwarfs, even the unusual ones, tend to follow some kind of pattern or occur under specific conditions. But this signal seemed to come out of nowhere with no apparent trigger or precursor. Some scientists speculate that it could have been caused by a rare and violent event, such as a collision between the brown dwarf and a passing object like an asteroid or comet. Such an impact could release a burst of energy, creating a signal that fades almost instantly. However, no evidence of such an event has been found, leaving this theory in the realm of speculation. Another possibility is that the phantom pulse was the result of an internal process within the brown dwarf itself. Brown dwarfs are known for their turbulent atmospheres and strong magnetic fields, which can produce a variety of emissions. It's possible that this signal was a one-time release of energy, perhaps from a magnetic reconnection event or a sudden flare. These phenomena are rare but not unheard of, and they could explain the signal's brief appearance. Yet, without additional observations, it's impossible to confirm whether this was the case. The mystery deepens when we consider the possibility that the phantom pulse might not have originated from the brown dwarf at all. Could it have been a signal from an entirely different source, passing through the same region of space at the exact moment the telescope was pointed in that direction? Space is filled with countless objects and phenomena, from distant galaxies to rogue planets, any of which could produce a fleeting signal. If this is true, the phantom pulse might not be a brown dwarf signal at all, but rather a cosmic coincidence that has led us down a fascinating but misleading path. What makes the phantom pulse particularly frustrating for scientists is the lack of follow-up data. Unlike other signals that repeat or leave behind traces, this one vanished without a trace. Efforts to detect it again have been unsuccessful, leaving researchers with only a single snapshot of its existence. This makes it nearly impossible to study in detail or draw definitive conclusions about its origin. It's a reminder of how much we still have to learn about the universe and the challenges of studying transient phenomena. Despite the unanswered questions, the phantom pulse has sparked important discussions about the nature of one-time signals in astronomy. It highlights the need for more advanced detection methods and continuous monitoring of the skies. Who knows what other fleeting signals might be out there waiting to be discovered? As we move forward, the phantom pulse serves as a tantalizing clue, urging us to keep searching for answers in the vast and unpredictable cosmos. And with that, we turn our attention to the next mystery, the resonant hum, a low-frequency signal that has captivated scientists with its unique and enduring presence. Now, as we delve deeper into the realm of one-time signals, it's worth exploring how the phantom pulse fits into the broader picture of astronomy. One-time signals, like the one we've just discussed, are not entirely unique in the cosmos. In fact, they represent a fascinating category of phenomena that challenge our understanding of the universe. These fleeting events, often detected only once and never again, are like cosmic whispers, brief, enigmatic, and packed with mystery. But what makes them so significant, and why do they captivate scientists and enthusiasts alike? One of the most famous examples of a one-time signal is the WOW signal, detected in 1977 by the Big Ear radio telescope. This powerful burst of radio waves lasted for 72 seconds and appeared to originate from the direction of the Sagittarius constellation. Despite numerous attempts to detect it again, the WOW signal has never been observed since. Its origin remains unknown, sparking debates about whether it could have been a message from an extraterrestrial civilization or simply a natural cosmic event. Like the phantom pulse, the WOW signal serves as a reminder of how much we still have to learn about the universe. Another intriguing example is the Lorimer burst discovered in 2007. This was a single, intense burst of radio waves that lasted just a few milliseconds. Initially, some speculated it could have been a technical glitch, but subsequent discoveries of similar bursts, now known as fast radio bursts, confirmed its cosmic origin. These bursts are thought to come from distant galaxies, possibly caused by cataclysmic events like neutron star collisions or black hole activity. Yet, their exact nature remains a puzzle, much like the phantom pulse. One-time signals are not limited to radio waves. In the field of gamma-ray astronomy, there are events known as gamma-ray bursts, or GRB, which are among the most energetic explosions in the universe. While some GRBs are observed multiple times, others are singular events, releasing an immense amount of energy in a matter of seconds before fading into oblivion. These bursts are thought to be linked to the collapse of massive stars or the merging of neutron stars, but their fleeting nature makes them difficult to study in detail. What makes one-time signals so important is their ability to reveal rare and extreme cosmic events. They act as cosmic messengers, offering glimpses into processes that are otherwise invisible to us. For instance, the detection of a one-time signal might indicate the presence of a previously unknown phenomenon, such as a new type of stellar explosion or an exotic object in space. These signals push the boundaries of our knowledge, forcing us to rethink our models and theories about how the universe works. However, studying one-time signals comes with its own set of challenges. Unlike recurring signals, which can be observed multiple times and analyzed in detail, one-time events leave scientists with only a single data point. This makes it difficult to draw definitive conclusions or rule out alternative explanations. It's like trying to solve a puzzle with only one piece. You can make educated guesses, but the full picture remains elusive. This is why advancements in technology, such as more sensitive telescopes and faster data processing systems, are crucial for detecting and understanding these fleeting events. The phantom pulse, along with other one-time signals, underscores the importance of continuous monitoring of the skies. Who knows what other rare and mysterious events might be out there waiting to be discovered? These signals remind us that the universe is full of surprises and that every observation, no matter how brief, has the potential to unlock new secrets. As we continue our journey through the mysteries of brown dwarfs, we now turn our attention to the resonant hum, a signal that stands in stark contrast to the fleeting nature of the phantom pulse, offering a steady and enduring presence that has intrigued scientists for decades. Now, shifting our focus to a signal that couldn't be more different from the fleeting phantom pulse, we encounter the resonant hum. Unlike the brief, one-time signals we've explored, this low-frequency hum detected from a brown dwarf in the Andromeda region is steady, persistent, and almost meditative in its consistency. It's a signal that doesn't just whisper, it resonates, creating a continuous background hum that has intrigued scientists for decades. What makes the resonant hum so unique is its frequency. Unlike the higher-pitched radio emissions or sudden bursts we've discussed, this hum operates at the lower end of the electromagnetic spectrum. It's a deep, almost imperceptible vibration that seems to emanate from the very core of the brown dwarf. This low-frequency signal is not only rare but also incredibly difficult to detect, requiring highly sensitive instruments and long observation periods to even register its presence. The Andromeda region, where this brown dwarf resides, adds another layer of intrigue. Andromeda is one of the most studied regions of the sky, home to countless stars, galaxies, and other celestial objects. Yet, amidst this cosmic cacophony, the resonant hum stands out as a singular phenomenon. Its steady rhythm contrasts sharply with the chaotic and unpredictable signals often detected in this region, making it a subject of intense curiosity. One of the most compelling aspects of the resonant hum is its potential connection to the internal dynamics of brown dwarfs. Scientists speculate that this hum could be linked to the magnetic fields or atmospheric turbulence within the brown dwarf itself. Imagine the interior of a brown dwarf as a swirling, turbulent environment where magnetic fields twist and interact, generating vibrations that ripple outward. These vibrations, when detected, manifest as the low-frequency hum we observe. It's a fascinating glimpse into the inner workings of these enigmatic objects. Another theory suggests that the resonant hum could be the result of interactions between the brown dwarf and its surrounding environment. For instance, if the brown dwarf is orbiting a companion star or passing through a dense region of interstellar gas, these external forces could create vibrations that produce the hum. This idea opens up a whole new realm of possibilities, as it implies that the signal might not be entirely intrinsic to the brown dwarf but influenced by its cosmic neighborhood. What truly sets the resonant hum apart, however, is its endurance. While many signals from brown dwarfs are fleeting or intermittent, this hum has been detected consistently over long periods. It's a signal that doesn't fade or falter, offering scientists a rare opportunity to study it in detail. This consistency makes it a valuable tool for understanding not just brown dwarfs, but also the broader mechanisms of low-frequency emissions in the universe. As we continue to explore the mysteries of brown dwarfs, the resonant hum serves as a reminder that the universe communicates in many ways, sometimes in fleeting whispers, and other times in steady, enduring tones. Its unique characteristics challenge us to refine our instruments and expand our understanding of these celestial objects. And as we turn our attention to the next signal, the intermittent beacon, we'll see how the universe continues to surprise us with its diversity and complexity. Now, let's take a closer look at the challenges scientists face when studying low-frequency signals like the resonant hum. Detecting these signals is no small feat. Unlike higher-frequency emissions, which are easier to pick up with standard radio telescopes, low-frequency signals require specialized equipment and long observation periods. The Earth's atmosphere itself can interfere, acting as a barrier that distorts or absorbs these faint vibrations before they ever reach our instruments. This makes the process of capturing and analyzing low-frequency signals a delicate and painstaking endeavor. One of the primary challenges lies in the sheer subtlety of these signals. Low-frequency emissions often blend into the background noise of the universe, making them difficult to distinguish from other cosmic phenomena. To overcome this, scientists rely on advanced filtering techniques and highly sensitive detectors, such as those used in the low-frequency array or LOFAR, which is specifically designed to pick up these elusive hums. Even with these tools, isolating a specific low-frequency signal from a brown dwarf requires patience and precision. So, where do these low-frequency signals come from? One leading theory points to the atmospheres of brown dwarfs themselves. These objects, often described as failed stars, have complex and turbulent atmospheres filled with swirling gases and powerful magnetic fields. As these magnetic fields interact with charged particles in the atmosphere, they can generate vibrations that ripple outward, producing the low-frequency hums we detect. It's a bit like the way a musical instrument creates sound, except in this case, the instrument is a massive, turbulent celestial body. Another potential source could be the interaction between a brown dwarf and its surroundings. For example, if a brown dwarf is orbiting a companion star or passing through a dense cloud of interstellar gas, the gravitational and magnetic forces at play could create vibrations that manifest as low-frequency signals. This idea suggests that the hum might not be entirely self-generated but influenced by the brown dwarf's environment, adding another layer of complexity to the puzzle. Studying these signals also opens up new avenues for understanding the broader universe. Low-frequency emissions aren't unique to brown dwarfs. They've been detected from other celestial objects, such as pulsars and even distant galaxies. By comparing these signals, scientists can uncover patterns and mechanisms that might be universal, shedding light on the fundamental processes that govern cosmic phenomena. Despite the challenges, the study of low-frequency signals is a field brimming with potential. Each detection, like the resonant hum, offers a glimpse into the inner workings of brown dwarfs and the forces that shape their behavior. As technology advances and our instruments become more sensitive, we may uncover even more of these hidden cosmic whispers, deepening our understanding of these enigmatic objects and the universe at large. And as we move forward, the next signal on our list, the intermittent beacon, promises to reveal yet another fascinating layer of this cosmic mystery. Now, shifting our focus to another intriguing signal, we encounter the intermittent beacon, a phenomenon that has left scientists both fascinated and perplexed. Unlike the steady hums or rhythmic pulses we've explored earlier, this signal behaves more like a flickering lighthouse in the vast ocean of space. It appears at random intervals, sometimes vanishing for years before suddenly reappearing, as if it's deliberately choosing when to make itself known. The intermittent beacon was first detected by the Very Large Array, one of the most powerful radio telescopes on Earth. What makes this signal so unusual is its unpredictability. While most cosmic emissions follow some kind of pattern or cycle, this one defies all expectations. It doesn't align with the rotational periods of brown dwarfs, nor does it seem tied to any known stellar activity. Instead, it comes and goes without warning, leaving researchers scrambling to capture and analyze it before it disappears again. So, what could be causing such erratic behavior? One theory suggests that the signal might be linked to extreme magnetic activity within the brown dwarf itself. Brown dwarfs are known for their powerful magnetic fields, which can sometimes produce bursts of energy. If these bursts are irregular or occur in response to internal instabilities, they could explain the sporadic nature of the intermittent beacon. Imagine a storm brewing deep within the brown dwarf, occasionally releasing bursts of energy that manifest as these fleeting signals. Another possibility is that the signal is influenced by external factors, such as interactions with a nearby object. If the brown dwarf is part of a binary system or is passing through a region of space filled with interstellar debris, these interactions could trigger sporadic emissions. For instance, a close encounter with another star or a dense cloud of gas might temporarily amplify the brown dwarf's magnetic activity, causing the signal to flare up before fading away once more. The irregularity of the intermittent beacon also raises questions about its potential significance. Could it be a natural phenomenon, or does it hint at something more deliberate? Some researchers have even speculated that such signals could serve as markers or beacons, intentionally designed to draw attention. While this idea remains highly speculative, it underscores the mystery surrounding these unpredictable emissions. Studying the intermittent beacon is no easy task. Its sporadic nature makes it difficult to predict when it will appear, requiring long-term monitoring and a bit of luck. Yet, each detection provides valuable data, helping scientists piece together the puzzle of brown dwarf behavior. As we continue to explore these enigmatic objects, signals like the intermittent beacon remind us just how much we still have to learn about the cosmos. And as we move forward, the next signal on our list, the echoing void, promises to take us even deeper into the mysteries of these celestial objects, revealing yet another layer of their complex and fascinating nature. Now, let's take a closer look at the concept of cosmic beacons and what they might mean for our understanding of the universe. The idea of beacons in space isn't new. Scientists have long speculated about the possibility of natural or artificial markers that could serve as signposts in the vast expanse of the cosmos. But what exactly makes a signal a beacon, and how might the intermittent beacon fit into this broader framework? In astronomy, A beacon is typically thought of as a signal that stands out from the background noise of the universe, something that draws attention due to its distinctiveness or regularity. Natural beacons could include phenomena like pulsars, which emit regular pulses of radiation, or even certain types of stellar flares. These signals are often predictable and can be used by astronomers to map the cosmos or study the properties of distant objects. But what about signals that don't follow a predictable pattern, like the intermittent beacon? Could they still be considered beacons, or do they represent something entirely different? One possibility is that the intermittent beacon is a natural beacon, but one that operates on a timescale or mechanism we don't yet fully understand. For example, it might be tied to rare or extreme events within the brown dwarf, such as massive magnetic storms or interactions with its environment. These events could produce sporadic bursts of energy that, while unpredictable, still serve as markers of activity. In this sense, the signal might not be a deliberate beacon, but rather a byproduct of the brown dwarf's complex and dynamic nature. On the other hand, the idea of artificial beacons opens up a realm of fascinating speculation. Could the intermittent beacon be a deliberate signal designed to attract attention or communicate across vast distances? While this idea is highly speculative, it's not without precedent. Scientists have long considered the possibility that advanced civilizations might use powerful signals to announce their presence or share information. If the intermittent beacon were artificial, its sporadic nature could be intentional, perhaps a way to conserve energy or avoid detection by unintended observers. Of course, the challenge lies in distinguishing between natural and artificial origins. Without a clear pattern or additional context, it's nearly impossible to determine the true nature of the intermittent beacon. This uncertainty is part of what makes studying these signals so exciting. Each detection offers a new piece of the puzzle, bringing us closer to understanding whether we're observing a natural phenomenon or something far more extraordinary. As we continue to explore the cosmos, the concept of beacons, whether natural or artificial, remains a compelling area of study. Signals like the intermittent beacon challenge our assumptions and push us to think creatively about the possibilities that lie beyond our current understanding. And as we turn our attention to the next signal, the echoing void, we'll delve even deeper into the mysteries of these enigmatic emissions, uncovering new insights into the behavior of brown dwarfs and the secrets they might hold. Now, shifting our focus to another intriguing signal, we encounter the echoing void, a phenomenon that has left scientists both puzzled and fascinated. This signal, detected from a brown dwarf in the Lyra constellation, stands out for its unique characteristic. It appears to echo itself, creating a repeating pattern that defies conventional explanations. Discovered by the Green Bank telescope during a routine survey, the echoing void immediately captured the attention of astronomers due to its rhythmic and almost musical quality. What makes this signal particularly intriguing is its structure. Unlike the chaotic or sporadic emissions we've discussed earlier, the echoing void follows a precise, repeating sequence. It begins with a strong burst of energy, followed by a series of diminishing echoes that mirror the initial pulse. This pattern repeats at regular intervals, creating a sense of rhythm that is rare in the natural emissions of brown dwarfs. The discovery has sparked a wave of curiosity as scientists grapple with the question, what could be causing such a precise and repeating signal? One leading theory suggests that the echoing void might be the result of interactions between the brown dwarf and its surrounding environment. For instance, if the brown dwarf is orbited by a dense cloud of gas or dust, the initial burst of energy could bounce off this material, creating the observed echoes. This would be similar to how sound echoes in a canyon, with the initial sound wave reflecting off surfaces to produce a repeating pattern. If this is the case, the echoing void could provide valuable insights into the composition and structure of the brown dwarf's surroundings. Another possibility is that the signal originates from within the brown dwarf itself. some researchers speculate that internal processes, such as magnetic field oscillations or plasma waves, could generate the repeating pattern. These phenomena, while not fully understood, might produce bursts of energy that resonate through the brown dwarf's atmosphere, creating the echoes we observe. If this theory holds, it could open up new avenues for studying the internal dynamics of these enigmatic objects. Of course, the echoing void also raises questions about its potential artificial origins. Could this repeating pattern be a deliberate signal designed to stand out against the background noise of the universe? While this idea remains speculative, it's worth noting that repeating signals have long been considered a hallmark of potential extraterrestrial communication. The echoing void's regularity and precision make it a prime candidate for such speculation, though natural explanations remain the more likely scenario for now. As we continue to study the echoing void, one thing is clear: this signal challenges our understanding of brown dwarfs and the mechanisms that govern their emissions. Whether it's a natural phenomenon or something more extraordinary, the echoing void invites us to explore the boundaries of our knowledge and consider the possibilities that lie beyond. And as we move forward, we'll delve deeper into the phenomenon of echoes in space, examining how they might occur naturally or through other means, and what they could reveal about the universe's hidden secrets. Now, let's take a closer look at the fascinating phenomenon of echoes in space and what they might reveal about the universe. Echoes, as we know them on Earth, occur when sound waves bounce off surfaces and return to the listener. But in the vast emptiness of space where sound cannot travel, echoes take on a different form. They manifest as repeating patterns of energy, like the ones we've observed in the echoing void. This raises an intriguing question. How do echoes occur in an environment where there's no air or solid surfaces to reflect energy? One natural explanation lies in the interaction between celestial objects and their surroundings. For instance, when a brown dwarf emits a burst of energy, that energy can interact with nearby clouds of gas, dust, or even magnetic fields. These interactions can cause the energy to scatter and reflect, creating a repeating pattern that resembles an echo. Think of it like a flashlight shining into a foggy night. The light scatters and reflects off the tiny water droplets, creating a glow that seems to linger. In space, the same principle applies, but instead of light, it's radio waves or other forms of energy that bounce back to us. Another possibility involves the internal dynamics of brown dwarfs themselves. These objects are known for their complex magnetic fields and turbulent atmospheres, which can generate bursts of energy that resonate within their structures. If a burst of energy is strong enough, it could create waves that travel through the brown dwarf's atmosphere, reflecting off internal layers and producing a repeating signal. This would be similar to how seismic waves travel through the Earth, bouncing off different layers and creating echoes that scientists can detect. If this is the case, the echoing void could be a window into the inner workings of brown dwarfs, offering clues about their composition and behavior. But what about the possibility of artificial origins? Could the echoing void be a deliberate signal designed to catch our attention? While this idea is speculative, it's worth considering. Repeating signals, especially those with precise patterns, have long been a focus in the search for extraterrestrial intelligence. The echoing void's rhythmic and consistent nature makes it an intriguing candidate for further investigation. However, it's important to approach this idea with caution, as natural explanations are still the most plausible at this stage. Echoes in space, whether natural or artificial, challenge our understanding of how energy behaves in the cosmos. They remind us that the universe is full of surprises, and even the most familiar phenomena can take on new forms in the vacuum of space. As we continue to study signals like the echoing void, we may uncover new insights into the mechanisms that govern these mysterious objects, and perhaps even stumble upon answers to some of the universe's biggest questions. Next, we'll explore another enigmatic signal that adds to the growing list of mysteries surrounding brown dwarfs, the silent storm. Now, let's turn our attention to a signal that seems to mirror the temperamental nature of the cosmos itself, the silent storm. This enigmatic signal emerges only during periods of heightened activity on brown dwarfs, vanishing completely during quieter phases. It's as if the brown dwarf itself is holding its breath, only to unleash a burst of energy when the conditions are just right. But what exactly triggers these outbursts, and what can they tell us about the turbulent environments of these celestial objects? The silent storm is closely tied to what scientists call stellar weather. Phenomena like flares, storms, and magnetic disturbances that occur on stars and brown dwarfs. Just as Earth experiences hurricanes and thunderstorms, brown dwarfs undergo their own versions of extreme weather, driven by their powerful magnetic fields and turbulent atmospheres. During these active periods, the brown dwarf's magnetic field lines can twist and snap, releasing enormous amounts of energy in the form of flares or bursts of radiation. It's during these moments that the silent storm signal is detected, appearing as a sudden spike in energy that fades away once the activity subsides. What makes the silent storm particularly intriguing is its silence during calmer periods. Unlike other signals that persist or recur, this one only appears when the brown dwarf is in a state of upheaval. This behavior suggests that the signal is directly linked to the internal dynamics of the brown dwarf, possibly arising from interactions between its magnetic fields and charged particles in its atmosphere. Imagine a lightning storm on Earth. The lightning only appears when the atmospheric conditions are just right, and once the storm passes, the sky returns to calm. The silent storm operates in a similar way, offering a fleeting glimpse into the chaotic processes at work within these mysterious objects. But the silent storm isn't just a curiosity, it's also a valuable tool for scientists studying brown dwarfs. By analyzing the timing, intensity, and frequency of these signals, researchers can gain insights into the internal structure and behavior of these objects. For example, the presence of such signals could indicate the strength and configuration of a brown dwarf's magnetic field, or even reveal the presence of hidden layers or features within its atmosphere. In this way, the silent storm serves as a kind of cosmic barometer, measuring the turbulent weather of distant worlds. As we continue to study signals like the silent storm, we're reminded of the dynamic and ever-changing nature of the universe. These bursts of energy, fleeting though they may be, offer a window into the inner workings of brown dwarfs and the forces that shape them. And while the silent storm may remain silent for now, its whispers could one day reveal secrets about the storms that rage across the cosmos. Next, we'll journey to the edge of the observable universe to explore a faint signal that challenges the limits of our detection, the distant whisper. Now, let's take a closer look at how stellar weather shapes the signals we detect from brown dwarfs. Stellar weather, much like the weather on Earth, is driven by dynamic and often chaotic processes. On brown dwarfs, this includes phenomena like powerful flares, magnetic storms, and atmospheric turbulence. These events are not just dramatic displays of cosmic energy, they also play a crucial role in generating the signals that capture our attention. Flares, for instance, are sudden bursts of energy that occur when magnetic field lines on a brown dwarf twist and snap, releasing vast amounts of radiation. These flares can produce intense signals, often appearing as sharp spikes in the data. But it's not just the intensity of these signals that matters, it's also their timing. Flares tend to occur during periods of heightened magnetic activity, which means they can act as markers for the underlying conditions on the brown dwarf. By studying these flares, scientists can piece together a picture of the magnetic environment and how it evolves over time. Magnetic storms, on the other hand, are more prolonged events that can last for hours or even days. These storms are driven by the interaction between the brown dwarf's magnetic field and its atmosphere, creating a turbulent environment where charged particles are accelerated to high speeds. This process can generate a variety of signals from steady hums to erratic bursts, depending on the intensity and duration of the storm. What's fascinating is that these signals often carry unique signatures, allowing researchers to identify specific types of storms and their effects on the brown dwarf's atmosphere. Atmospheric turbulence also plays a key role in shaping the signals we observe. Just as wind and pressure systems create weather patterns on Earth, the movement of gases and charged particles in a brown dwarf's atmosphere can produce fluctuations in signal strength and frequency. These fluctuations can reveal details about the structure and composition of the atmosphere, as well as the forces driving its behavior. For example, a sudden drop in signal intensity might indicate the presence of a dense cloud or a region of high pressure, while a rapid increase could signal the onset of a storm or flare. What ties all of this together is the interplay between the brown dwarf's magnetic field and its atmosphere. The magnetic field acts as a kind of conductor, channeling energy and particles through the atmosphere and creating the conditions for stellar weather. This interaction is what gives rise to the signals we detect, from the fleeting bursts of the silent storm to the rhythmic pulses of other emissions. By studying these signals, we're not just observing the weather on brown dwarfs, we're uncovering the fundamental processes that govern their behavior. As we continue to explore the connection between stellar weather and signal emissions, we're reminded of the complexity and beauty of these celestial objects. Each signal tells a story, offering clues about the forces at work within brown dwarfs and the broader universe. And while the storms and flares may seem chaotic, they are part of a larger pattern, one that we are only beginning to understand. Next, we'll venture to the edge of the observable universe to uncover a faint signal that challenges the limits of our detection, the distant whisper. Now, let's turn our attention to one of the most intriguing signals yet, the distant whisper. This faint signal was detected from a brown dwarf located at the very edge of the observable universe, a place so remote that it pushes the boundaries of our detection capabilities. What makes this signal so remarkable is not just its distance, but the fact that it managed to reach us at all. The sheer vastness of space means that signals from such distant objects are often lost or weakened by the time they reach Earth. Yet the distant whisper persisted, offering a rare glimpse into the far reaches of the cosmos. The significance of this signal lies in what it tells us about the universe itself. Detecting a signal from such a distant brown dwarf is like hearing a whisper across a crowded room. It's a testament to both the sensitivity of our instruments and the enduring nature of these emissions. This brown dwarf, located billions of light years away, represents a snapshot of the universe as it existed in its earlier stages. By studying its signal, we're essentially looking back in time, uncovering clues about the conditions and processes that shaped the cosmos in its infancy. However, studying such distant objects comes with its own set of challenges. One of the biggest hurdles is the signal's faintness. As light and other forms of radiation travel across the universe, they are stretched and weakened by the expansion of space, a phenomenon known as redshift. This means that by the time the distant whisper reaches us, it's often just a fraction of its original strength. Detecting and analyzing these faint signals requires incredibly sensitive equipment and sophisticated techniques to filter out background noise and interference. Another challenge is the sheer distance involved. The farther away an object is, the harder it is to gather detailed information about it. Even with the most advanced telescopes, the distant whisper appears as little more than a faint blip in the date. This makes it difficult to determine the exact nature of the brown dwarf or the processes that produce the signal. Is it a result of stellar weather, like the storms and flares we've discussed earlier? Or could it be something entirely new, a phenomenon we've yet to understand? These are the questions that keep scientists intrigued. Despite these challenges, the distant whisper holds immense potential for advancing our understanding of the universe. It serves as a reminder of how much we still have to learn about the cosmos and the objects within it. Each faint signal we detect, no matter how distant or weak, adds another piece to the puzzle, helping us build a more complete picture of the universe's history and evolution. As we continue to push the boundaries of our detection capabilities, signals like the distant whisper will play a crucial role in shaping our understanding of the cosmos. They remind us that even the faintest whispers can carry profound insights, if only we have the tools and patience to listen. Next, we'll delve into the chaotic symphony of frequencies that defy explanation as we explore Signal 13, the chaotic symphony. Now, let's take a closer look at the technological challenges that come with detecting signals as faint and distant as the distant whisper. One of the biggest hurdles is the sheer sensitivity required to pick up these signals. Even with our most advanced telescopes, the faint emissions from brown dwarfs at the edge of the observable universe are often drowned out by cosmic noise, background radiation from stars, galaxies, and other celestial phenomena. This makes isolating and identifying these signals a bit like trying to hear a single instrument in a symphony playing at the very edge of your hearing range. To overcome this, scientists rely on cutting-edge technology and innovative techniques. For example, radio telescopes like the Very Large Array and the upcoming Square Kilometre Array are designed to detect incredibly weak signals by combining data from multiple antennas. This process, known as interferometry, allows astronomers to amplify faint emissions and filter out interference. However, even with these tools, the signals from distant brown dwarfs remain incredibly challenging to study. The farther away the object, the more the signal is stretched and weakened by the expansion of the universe, a phenomenon known as redshift. This means that by the time the signal reaches us, it's often just a whisper of its original strength. Another limitation is the resolution of our instruments. While we can detect faint signals, determining their exact source or nature becomes increasingly difficult with distance. A brown dwarf billions of light years away might appear as little more than a faint blip in the data, making it hard to gather detailed information about its composition, magnetic fields, or activity. This lack of resolution limits our ability to fully understand the processes behind these signals and whether they're caused by natural phenomena or something more mysterious. Advancements in technology, however, are offering new hope. For instance, machine learning algorithms are being developed to sift through vast amounts of data more efficiently, identifying patterns and anomalies that might otherwise go unnoticed. These tools could help astronomers pinpoint faint signals with greater accuracy, even in noisy datasets. Additionally, future telescopes with higher sensitivity and resolution, such as the James Webb Space Telescope and the Extremely Large Telescope, promise to bring distant brown dwarfs into sharper focus, potentially revealing new details about their emissions and behavior. But it's not just about better instruments, it's also about how we use them. Collaborative efforts between observatories around the world are enabling longer observation times and more comprehensive data collection. By pooling resources and expertise, scientists can tackle the challenges of detecting faint signals more effectively, pushing the boundaries of what we can observe and understand. As we continue to refine our technology and techniques, signals like the distant whisper may become less of a mystery and more of a window into the universe's deepest secrets. Each advancement brings us closer to unraveling the complexities of these faint emissions and the distant objects that produce them. Next, we'll explore a signal that defies all patterns, a chaotic mix of frequencies that has left scientists scratching their heads. This is Signal 13, the chaotic symphony. Now, shifting our focus to a signal that seems to defy all logic, we arrive at Signal 13, the chaotic symphony. Unlike the rhythmic pulses or harmonic echoes we've explored so far, this signal is a jumble of frequencies, a cacophony of cosmic noise that refuses to follow any discernible pattern. Discovered by the Green Bank Telescope in West Virginia, this chaotic emission has left scientists both fascinated and perplexed. It's as if the universe decided to play every note on a cosmic piano at once, creating a soundscape that's impossible to decode. The chaotic symphony was first detected during a routine survey of brown dwarfs in the Milky Way. At first, astronomers thought it might be interference from Earth-based sources like satellites or radio towers. But after extensive analysis, they confirmed that the signal originated from a brown dwarf located approximately 100 light-years away. What makes this signal so unusual is its lack of structure. While most emissions from brown dwarfs show some form of regularity, whether it's a steady hum, a rhythmic pulse, or a repeating pattern, this one is entirely unpredictable. Its frequencies shift rapidly, sometimes overlapping, sometimes dropping out entirely, creating a chaotic blend that defies explanation. So, what could be causing such a disordered signal? One leading theory points to extreme magnetic activity on the brown dwarf's surface. Brown dwarfs are known for their powerful magnetic fields, which can generate intense flares and storms. These magnetic disturbances could potentially produce a chaotic mix of radio emissions, as charged particles interact with the magnetic environment in unpredictable ways. Another possibility is that the signal is the result of interactions between the brown dwarf and a nearby object, such as a planet or a companion star. These interactions could create turbulence in the brown dwarf's atmosphere, leading to erratic emissions. However, not all scientists are convinced by these natural explanations. Some have speculated that the chaotic symphony could be evidence of something more extraordinary, perhaps even artificial in origin. While this idea remains highly controversial, it's hard to ignore the fact that the signal's randomness stands out so starkly from the typical emissions of brown dwarfs. Could it be a form of communication or even a byproduct of advanced technology? For now, this remains purely speculative, but it's a tantalizing thought that keeps researchers digging deeper. As we continue to study the chaotic symphony, one thing is clear. It challenges our understanding of brown dwarfs and the signals they produce. Whether it's the result of natural magnetic phenomena, interactions with other objects, or something entirely unexpected, this chaotic signal reminds us that the universe is full of surprises. And as we move forward, we'll explore another signal that has remained consistent for decades, defying expectations of variability. This is signal 14, the timeless pulse. Now, let's take a closer look at the concept of chaos in astrophysics and how it might explain signals like the chaotic symphony. Chaos, in scientific terms, refers to systems that are highly sensitive to initial conditions, making their behavior unpredictable over time. In space, chaos can arise from a variety of factors, such as gravitational interactions, magnetic fields, or even the turbulent atmospheres of celestial objects like brown dwarfs. These chaotic systems can produce signals that appear random or disordered, much like the jumble of frequencies we've observed in the chaotic symphony. One way chaos manifests in astrophysics is through the complex interplay of magnetic fields and charged particles. Brown dwarfs, with their intense magnetic activity, are prime candidates for such chaotic behavior. Imagine a storm on Earth where winds and pressure systems interact in unpredictable ways. On a brown dwarf, magnetic storms can create similar turbulence, generating bursts of energy that fluctuate wildly. These bursts might overlap, cancel each other out, or combine in unexpected ways, leading to the chaotic signals we detect. Another factor contributing to chaos in space is the presence of multiple interacting objects. For example, if a brown dwarf has a nearby planet or companion star, their gravitational pull can disrupt the dwarf's atmosphere or magnetic field. This disruption can create irregular patterns in the emissions, adding another layer of unpredictability. Think of it like ripples in a pond when multiple stones are thrown in at once. The waves interfere with each other, creating a complex and chaotic surface. Interestingly, chaos isn't always a sign of disorder. In some cases, it can reveal underlying patterns or processes that aren't immediately obvious. scientists use mathematical models and simulations to study chaotic systems, hoping to uncover hidden rules or structures. For the chaotic symphony, researchers are exploring whether the signal's randomness might actually follow a deeper, more complex pattern that we haven't yet identified. This could open up new ways of understanding how brown dwarfs behave and how their emissions are generated. While chaos in space can be challenging to study, it also offers a fascinating glimpse into the dynamic and ever-changing nature of the universe. The chaotic symphony reminds us that even in the vastness of space, there are phenomena that defy our expectations and push the boundaries of our knowledge. As we continue to unravel the mysteries of brown dwarfs, signals like this one will undoubtedly play a key role in shaping our understanding of these enigmatic objects. With that in mind, let's turn our attention to a signal that stands in stark contrast to the chaos we've just explored. Signal 14, the timeless pulse, has remained remarkably consistent for decades, offering a different kind of mystery, one that challenges our assumptions about variability in the cosmos. Now, shifting our focus to a signal that defies the chaos we've just explored, let's dive into Signal 14, the timeless pulse. Unlike the unpredictable and erratic emissions we've seen in other brown dwarf signals, this one has remained remarkably steady for decades. Detected for the first time in the late 1980s, the timeless pulse has continued to emit a consistent, unchanging signal, challenging our understanding of how brown dwarfs behave over time. At first glance, this consistency might seem unremarkable, but in the context of brown dwarfs, it's anything but ordinary. These celestial objects are known for their dynamic and often volatile activity, with magnetic storms, atmospheric turbulence, and interactions with nearby objects causing their emissions to fluctuate. Yet the timeless pulse stands out as an anomaly, maintaining its rhythm without any noticeable changes. This raises a fascinating question. What could be causing such unwavering stability in an environment that's typically so chaotic? One possibility is that the timeless pulse originates from a particularly stable region within the brown dwarf's atmosphere or magnetic field. Imagine a calm eye in the middle of a storm, where conditions remain steady despite the surrounding turbulence. If such a region exists, it could act as a constant source of emission, producing the unchanging signal we observe. Alternatively, the signal might be tied to a long-term process within the brown dwarf itself, such as a slow but steady release of energy from its core or a stable interaction with a nearby object. Another intriguing aspect of the timeless pulse is what it tells us about the lifespan of brown dwarfs. These objects, often referred to as failed stars, occupy a unique place in the cosmic hierarchy. They're not massive enough to sustain nuclear fusion like stars, but they're too large to be classified as planets. The timeless pulse suggests that some brown dwarfs may have periods of stability that last for decades or even longer, offering a glimpse into their long-term behavior. This could help scientists refine models of how brown dwarfs evolve over time and how they interact with their surroundings. The consistency of the timeless pulse also has practical implications for astronomers. Unlike erratic signals that are difficult to study due to their unpredictability, this steady emission provides a reliable benchmark for observations. It allows researchers to track changes in other aspects of the brown dwarf, such as its rotation or magnetic activity, without the interference of a fluctuating signal. In a way, the timeless pulse acts as a cosmic metronome, keeping time in the otherwise chaotic symphony of brown dwarf emissions. As we continue to study this enigmatic signal, it challenges us to rethink our assumptions about variability in the cosmos. The timeless pulse reminds us that even in a universe filled with chaos and unpredictability, there are still pockets of stability waiting to be discovered. And as we uncover more about this signal, it may hold the key to unlocking new insights into the nature of brown dwarfs and their place in the grand tapestry of the universe. With that, let's turn our attention to the next signal, which takes us in a completely different direction, a faint whisper from the edge of the observable universe, where the mysteries of space grow even deeper. Now, as we delve deeper into the significance of the timeless pulse, it's impossible to overlook the critical role of long-term observations in unraveling the mysteries of brown dwarfs. Unlike fleeting signals that vanish as quickly as they appear, the timeless pulse has been a constant presence in the data for decades, offering scientists a rare opportunity to study these enigmatic objects over extended periods. This kind of sustained observation is invaluable because it allows researchers to track subtle changes and patterns that might otherwise go unnoticed. Long-term studies of brown dwarfs have revealed behaviors that challenge our existing models. For instance, while many brown dwarfs exhibit erratic activity, the timeless pulse demonstrates that some can maintain remarkable stability over time. This discovery has forced astronomers to reconsider the factors that influence brown dwarf emissions, such as their internal dynamics, magnetic fields, and interactions with their surroundings. By observing these objects over years or even decades, scientists can piece together a more comprehensive picture of their life cycles and evolutionary paths. One of the key benefits of long-term observations is the ability to distinguish between short-term anomalies and consistent phenomena. In the case of the timeless pulse, its unwavering signal stands in stark contrast to the more chaotic emissions typically associated with brown dwarfs. This consistency has allowed researchers to rule out certain explanations, such as transient events or external interference, and focus on more enduring processes. It's a reminder that patience and persistence in observation can yield insights that quick snapshots simply cannot provide. Moreover, long-term data collection enables scientists to identify trends and correlations that might otherwise remain hidden. For example, by comparing the timeless pulse with other signals from brown dwarfs, researchers have begun to uncover patterns that could shed light on the underlying mechanisms driving these emissions. These findings not only enhance our understanding of brown dwarfs, but also contribute to broader astrophysical knowledge, such as the behavior of magnetic fields in celestial objects and the dynamics of stellar atmospheres. The timeless pulse also underscores the importance of technological advancements in long-term observation. Over the decades, improvements in telescopes, detectors, and data analysis techniques have allowed astronomers to monitor signals like this one with unprecedented precision. As technology continues to evolve, it's likely that even more subtle and complex behaviors will be revealed, further expanding our understanding of brown dwarfs and their place in the universe. In essence, the timeless pulse serves as a testament to the power of long-term observation in astronomy. It reminds us that some of the universe's most profound secrets are revealed not in moments of dramatic change, but in the quiet, steady rhythms that persist over time. As we continue to study this signal and others like it, we inch closer to unlocking the mysteries of brown dwarfs and the cosmic processes that shape them. And with that, let's turn our gaze to the next signal, a faint whisper from the edge of the observable universe where the mysteries of space grow even deeper. As we reach the end of our journey through these 25 unexplained signals from brown dwarfs, one thing is clear: the universe is far more mysterious and complex than we often imagine. From the whispering giant to the timeless pulse, each signal has challenged our understanding of these celestial objects and left us with more questions than answers. What causes these strange emissions? Are they the result of natural phenomena we have yet to uncover, or could they hint at something even more extraordinary? The possibilities are as vast as the cosmos itself. These signals remind us that there is still so much we don't know about the universe. They invite us to keep exploring, to keep questioning, and to remain curious about the wonders that lie beyond our planet. Whether it's the rhythmic pulses of the pulsating enigma or the eerie silence of the silent scream, each signal tells a story that pushes the boundaries of science and imagination. And while we may not have all the answers yet, the pursuit of understanding is what drives us forward. Now, it's your turn to join the conversation. What do you think these signals could mean? Do you have a theory about their origins or purpose? Share your thoughts in the comments below. We'd love to hear your ideas and theories. And if you're as fascinated by brown dwarfs and the mysteries of space as we are, don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss an update. Together, let's keep exploring the incredible, uncharted depths of the universe. Thanks for watching, and until next time, keep looking up.